right, we are back to do some more differential equations. So today we are going to learn why the heck are you learning Laplace transforms. Okay, so one of the things we're going to use with them is we're going to solve DEs using Laplace transforms. Okay, now there's a couple of different ways we write differential equations, right? We write f prime of t, right, aka y prime. Okay, so those are different ways of doing this, and we're going to I'm going to slip in between using both of these. We could also say y of t, okay, or whatever variable we happen to be using here. Okay, so we're going to take the we're going to wonder, like, what is this idea? Okay, what is the Laplace transform, or right, what is the Laplace transform of y prime? Okay, same question. Well, there's a couple of things we have to kind of get in order here. We are going to assume that the Laplace transform of y prime, right? We're going to assume that this exists, okay? If we have reason to believe it doesn't, and we're going to learn some in chapter 4, then this is the wrong technique, and we're going to do something different, okay? We're also going to assume that y exists, right? That if we took the derivative of a function, right, we have this. Presumably, there's a function we took the derivative of, right? So if we have this, y prime, assuming there's a y, okay, we also kind of have to know that y of 0 equals something, okay? It doesn't have to be really that known, but this is going to be a given in your problems, okay? So y of 0 is going to be a given, okay? So the idea that I think we also need that the Laplace transform of y is equal to integral e to the infinity, right? Or not e to the infinity, or 0 to infinity, e to the negative st times y, okay? Or, right, equivalently, depending on how we write it, that there's some kind of an ft. Okay, and we're going to say that the Laplace transform of this thing, that again, we don't know exactly what it is. This is what we're solving for. That we're going to call it either y of s or f of s. Okay, that's how we're going to write this down. Okay, I guess you could just call it y, but but that's generally how I write it. Okay, so with that out of the way, okay, so as a lot, we're assuming that if we have a derivative of a function, that the original function exists. We have to be told what the initial condition is, and we're going to be solving for it, but we're also assuming that the Laplace transform of this thing does exist. Okay, but why are we bothering to prove the rest of this? Here we go. Okay, so we've got the Laplace transform, right, of y prime, or f prime rather, of t. Well, definition-wise, right? 0 to infinity, e to the negative st times f prime of t. We have two functions multiplied by each other inside of an integral. This is an integration by parts problem. So what we're going to do here is we're going to say, well, how about u is equal to e to the negative st, du, right, is equal to negative s e to the negative st. dv is equal to f prime of t. See, here's one of those assumptions. We took the derivative of a function and got f prime. I'm going to assume, right, that f exists for us to take a derivative of in order to get this. All right. So there we go with that. Okay. And we can just go ahead and multiply. So it's going to be uv, right? So this is going to be e to the negative st f of t, okay, minus integral of negative s e to the negative st, right, f of t. All right, so here we go. So this is going to be e to, there's always dt's in here, negative e to the st, right, ft, plus, right? And then we have, I'm going to pull this s because it's a parameter. We're integrating with respect to t, so this is a constant, right? S is a constant. E to the negative st, and then we have f of t dt, 0 to infinity. Okay, and then we have to evaluate. Okay, so let's go ahead and take our limit. So we have e to the negative s. I'm going to use a capital T for the limit as t goes off to infinity, right? F of t minus e to the negative s times 0, f of 0. Okay, that's this piece right here. Okay, plus s. We'll come back to this cheese in a minute here. Okay. So as t goes off to infinity, right? So well, what if f doesn't have a limit? Like, well, part of the way if we take the Laplace transform is that we've assumed that the functions we're taking the Laplace transforms of have, right, or of exponential order. So this, again, this limit exists. If it doesn't, you can chuck the whole thing out because nothing works. Okay. But if this limit exists, then the e to the negative st, that's 0. Okay. Minus e to the s0, that's 1. So we just have f of 0 here. Okay. Plus s. Now, please forgive me for this. E to the negative st, right, times f of t, isn't that y of s, right, or f of s? Yeah, that's the thing. We know what this is. So this is just s times f of s. Okay, so the Laplace transform of f prime of t is equal to s fs minus f of 0. Equivalently, right, if I want to take the Laplace transform of y prime, again, this is what we're going to be solving for. Actually, this is what we're going to be solving for. I'm going to write it s y of s minus y of 0. Okay, so I'm going to go back and forth between these two notations. Different books use different ones, but they're equivalent, the same. Okay, but that is the Laplace transform of the first derivative. You want to see the second derivative? I know you did. So Laplace transform of y prime, right, double prime, okay? And again, for this one, we need to have an assumption. We need to know that y prime of 0 is equal to something, okay? We have to have an initial condition. Okay, we're going to pull the same kind of trick on this as we did on the previous. It's not really a trick. It's just we set things up so that we would get the answer that we wanted. Okay, so here we go. We have like a Laplace transform, right, of y double prime. This is equal to integral from 0 to infinity e to the negative st times, right, f double prime of t. Again, we have a function times a function inside of an integral. That's integration by parts. So u is equal to e to the negative st. Du is equal to negative s e to the negative st. dv is equal to f double prime of t. Okay. Now again, we have a second derivative here. Presumably, there was a first derivative that we took. We took this derivative of this function in order to generate that one. So going out on a limb here and saying this thing exists. Okay, it's not much fun. Okay, so here we go, right? It's UV, it's this thing, times, it's the diagonal times the bottom here. So this is e to the negative st, f prime of t, minus integral negative s, e to the negative st times f prime of t, dt. Let's clean this up a little bit, right? So this is e to the negative st, f prime of t, that we're going to be evaluating, right, from 0 to infinity. Negative times negative is positive, so plus s integral e to the negative st, f prime of t. Okay, so as we evaluate, right, we have e to the negative s capital T, that's the limit, as t goes off to infinity here. f prime of capital T, again, limit. But same thing, right, is that we assumed these things are of exponential order. Exponential order, all right, polynomials, right, if you have a polynomial, their derivatives are also of exponential order because you also have a polynomial. You can't escape. Exponential functions, right, so including hyperbolic sines and cosines. So we can always pick an S that this term will go to 0 faster than the exponential function we were given. Okay. Logarithms, well, logarithms aren't, because at 0 they don't have a limit. Okay. Let's see here. What are we doing? And sine and cosine. Okay, and again, you take the derivative of sine, you get cosine. You take the derivative of cosine, you get negative sine. So these are generally your exponential order functions. Polynomials, exponential functions, sine, cosine. These happen a lot. Okay, there's a lot of differential equations that just deal with solutions like this. Okay, and again, there are some exceptions. We're going to learn about those a little bit later. All I can tell you is that the procedure for that is delightful. But all of these derivatives are also of exponential order. So going out and saying this is of exponential order, not much of a stretch. Okay, so this term is going to dominate, that's 0. Okay, minus e to the negative s times 0, f prime of 0, minus f prime of 0. See, that's why we need, and again, this is going to be given. Okay, they're going to tell you this. Okay, now, this is plus s integral at 0 to infinity e to the negative st f prime of t. Haven't I seen this somewhere before? Like, isn't this the Laplace transform of f prime? It is the Laplace transform of f prime. So what was the Laplace transform of the first derivative? Right? This was s, y of s minus y of 0. So we're going to write down, this was s, y of s minus f of 0. Okay, so here we go. We have negative f prime of 0 plus, that's s squared, y of s minus s f of 0. Let's rewrite this so it looks a little bit nicer. S squared y of s minus s f of 0 minus f prime 0. Okay, that's the Laplace transform of y double prime of t. Okay, now let's just go with this for just a moment. Okay, I believe this table actually has both of them. So f prime of t, right? And again, this is a table you're going to have access to, so you do not have to memorize it. You're just going to get real familiar with the stuff at the bottom, because that's what you're going to write in here. Okay, 36, this was f double prime, s squared, f of s minus s, f of 0 minus f prime of 0, just like we did. And in the unlikely event, okay, and I say unlikely knowing full well that you've got at least one example, one homework problem where it's a triple, it's a f cubed, or f, not cubed, third derivative, that you're going to have to untangle this. Okay, there's not too many. These problems tend to be a little on the long side, so it's unlikely I would ask you a difficult third derivative problem, third order differential equation. That I used to, like the first couple of times I taught the class, I would do that. And then most of my students, were also taking classes over at UNM. They asked their friends in DE there, and they said, we don't do third order. It's like, okay, well, I don't see any reason for me to be forcing you to do third order as well. So that kind of stopped. But there are some easy ones to pick. So it's not, you're not off the hook forever and always. I'm not going to promise I'm never going to give it to you, one of these, but I will promise that it will be it'll be carefully picked, carefully chosen, so that it's not the worst mess in the world. Again, not it's also, there's one in the homework that is just, it's awful. Okay, I'll walk you through it, but I will warn you, it is terrible. All right, I think I have a little bit of time to do one. Let's do one problem where we actually solve a differential equation, okay? So finally, it's like what this class is all about. So let's pick one that you know how to do, okay? Let me do this for a moment so I can find the paper. Okay, back to where it is. So we have y prime plus 3y is equal to e to the 5t. We're going to use the table to help us out here. Okay. We were also told that y of 0 is what here? Because you have to be told this. Okay. Y of 0, I believe, is 1. Okay. Double check, making sure that. Yeah, I think that's what it was. Okay. So this is a first order linear equation, isn't it? So you could technically solve this in a number of ways, specifically getting a integration factor, right? Where rho is equal to e to the 3 integral dt, rho is equal to e to the 3t, multiply that through, and then go through and deal with that. No problem, right? The reason why we're doing it this way is like, well, isn't there an easier way to solve it? Like, yes, but I want you to solve it this way with this one so that you know you got the right answer, because you could always check. So what is the Laplace transform of y prime? So we're going to go to our table. We're going to say, f prime of t, s, f of s minus f of 0. Okay. So we have, this is Laplace. So we're taking Laplace transform. Let's just do it this way. Okay, we're taking Laplace transform both sides. Okay. So we have s, I'll use y of s minus y of 0. Okay, that's this term. Plus 3, taking the Laplace transform of y. Don't know what it is, it's y of s. Okay, is equal to, what's the Laplace transform of e to the t? Well, let's go back up here and say, well, e to the at is 1 over s minus a. So this is 1 over s minus a, 5. Okay, so we're going to go ahead and say, well, this is s, y of s, minus 1 plus 3 y of s is equal to 1 over s minus 5. Okay, let's go ahead and combine some terms here, clean things up. So here we have s, y of s plus 3 y of s is equal to 1 over s minus 5 plus 1. Okay. Now, you have some options here. What I would recommend at this point is that you get a common denominator, okay? Because we're going to have to do some partial fractions in a moment here. And if there's anything that's more fun about doing one partial fractions problem, it's doing two partial fractions problems. So let's keep it to 1. So this is going to be s minus 5, isn't it? Okay, so this is going to be y of s, common, right? What's left? S plus 3. This is equal to 1 over s minus 5 plus s minus 5, s minus 5. Okay, so what's that going to give us? That's going to give us s minus 4, right? Minus 5 plus 1 over s minus 5. So we're going to have s there is equal to s minus 4 over s minus 5, s plus 3. Okay. Now I don't have an inverse Laplace transform that does this. Okay. Look, there is no like s minus a, s minus b. There isn't any of those. So we have to do partial fractions here. There's going to be a lot of partial fractions. Okay. So what we're going to do here is we're going to say this is equal to an a over an s minus 5 plus a b over an s plus 3. I'm just going to do this the long way. Yes, there is a shortcut. Yes, you're allowed to use it. Okay. Yes, you could even plug this into a calculator and use the matrix solver in the calculator. Okay. This is not about solving a whole bunch of partial fractions problems. Okay. But for this problem, because it's small, I'm just going to go ahead and do it the old-fashioned way. Right. And this is equal to s minus 4. Okay. All I did was clear the fractions here. So by inspection, I'm going to say that my s terms, right, we have an a plus a b, these would all have an s in them, is equal to, there's one s over here. Okay. My constant term, okay, there would be 3 a's minus 5 b's, right, and this is equal to -4. Okay. And all we have to do now is solve this system of equations. Okay. Why don't we multiply this thing by -3? So it's -3a minus 3b is equal to -3. We have 3a minus 5b is equal to -4. Okay, let's go ahead and add. So that's going to be -8b is equal to, we're adding, so that's -7. B is equal to 7/8. Okay. A would be 1/8. Right, because a plus b has to be 1. 7/8, negative over negative. 7/8 plus 1/8 would be 8/8. Okay. So what did we say this thing was? We said this was 1/8 times 1 over, what is that, s minus 5? 5. Okay, plus 7/8, 1 over s plus 3. This is equal to y of s. All right, now we do have this set up, so we're going to take inverse Laplace transform both sides. This just goes back to be y of t. This was the whole goal, right? Like from the beginning of the class, the goal was to like solve for y. We're going to get a function. What's y? This is 1 over 8 e, right? S minus a. Okay, a is 5 in this case. So s minus e to the 5t plus 7/8. Okay, this is e. This is a negative rate. This is negative negative. So this is s minus a -3. So this is e to the -3t. So there is our solution to this differential equation. Okay, I promise you they get harder. I promise you there will be times when you're like, I'm glad I have this technique because there's no way I am solving this in any other way. Okay, you can verify this with the with your integration factor. Don't forget to plug in for your c because your y of 0 is equal to 1, and then you can go through from that. Okay, so I'm going to put this down. We're going to do 7.2 soon, and we'll learn how to solve some of these. Okay, very good.